Okay, that's set up. Good. So two things, or maybe three things. A, we need to make up. But before that, this Wednesday, we won't have a regular class because I'm traveling. Okay. So, and then we talked about either Tuesday, Thursday, Friday option. Friday is not an option because I'm traveling. So, and then I figured out that after this week, next week, and the week after is final exam week, yes? Woohoo. And by the way, we will have a final exam, some fun. It's not really for, it's not getting recorded. Yes, it is for, evaluation and 10 years now. Okay, just have some fun. So we will have final exam. I haven't thought about it, what's going to be, but something that we talked about during the class. Okay, some creativity, some calculation, some concept. Anyway, so so we need to make up next week. Next week, I'm traveling from Tuesday till Saturday or something. So next Monday we will have a class. By the way, next Monday is what? December 4th, am I right? Yeah. Yes. So this Wednesday, no class. Next Wednesday, no class. So we need another makeup for those, and then I missed two because I traveled to China. So that means looks like we will have to make up a lot this week. Good for you, good for me. Like I have to give 5 lectures this week or something like that. So there are two options. Option number one, we have a one makeup this week and then another makeup next Monday evening. Okay, that's option number one. And most likely this week, Thursday evening will be one option. Who cannot do Thursday evening again? Okay, well, we will record it so you can watch it in case you cannot. And then option number two, we have makeup this Tuesday, this Thursday. So I'm dead after that, but anyway, that can be done. And then next Monday, just one class during the regular time. So option number one makeup this Thursday, and then another makeup next Monday. That's option number one. Option number two, let's have like that week. Okay, Tuesday, Thursday, we just hammer it. And then next Monday is going to be our last lecture. So, okay, with blood. Okay, so who likes to have option number one? Two makeup this, oh man, you guys bloody. Okay, who wants it? Oh, wait, no. You guys are kind, okay? So no, one here, next one. Okay, that's option number one. Who wants to have, okay, option number one. Option number one, okay. Okay, good. Option number two, let's like do it this week. Okay, so this is secretly personality test. So I'm sorry, I got you. So by majority vote, so we will have one makeup this Thursday evening, and then another one next Monday evening. Okay, and then we will have roughly two sessions combined into one. So maybe I don't know, a little bit longer than 12, two and a half, or maybe 3, depending on how things go. Okay. All right. So we will post exact time, but it's going to be this Thursday evening, the first makeup, and the second makeup next Monday evening. Okay. Good. And then after this class, I will post the homework problem. So I'm really sorry that I did not give you enough homework that you can enjoy, right? You've been looking for homework so much. So sorry for that. So now I'm gonna throw out homeworks. So I will give one homework this week, another homework next week, but due date will be by the end of the final exam. Okay? So most likely I will just ask you to do some of the problem from the Coleman and think through some of the sessions that I didn't cover. Okay? I did. I learned it. No, I learned it. Very good. Okay, so with that, so clear. So announcement together. Let me repeat. This Wednesday, no class. Next Wednesday, no class. Okay, so we will have a one makeup by which I mean roughly 3-hour-long makeup this Thursday evening. Second makeup is going to be next Monday evening. Okay, and then there will be homeworks you should expect, and then we will have a final with them. Any question? Sorry? The class. Good question. So maybe 7:30. How does that sound? Does 7:30 sound okay? Okay, good. Very good. So 7:30. I know I have another meeting with the people in the US 10:30, so we can run 3 hours, and then I go to the Zoom meeting. Good. Let's get to the discussion now. Any question about physics or any other question? Any question? Good.
혹시 과제는 좀 늦게 내실 생각이신가요?
How many homework problems that you mean? Maybe one set after this class I'm gonna post. Again, you will be asking mostly just to do some of the problems from the Coleman's book, and then read the sections that I didn't cover explicitly during the section, and then present your own opinion and understanding about it. Okay, and another one next week. Similar kind. Okay. So good. So we covered CPT and then what? Crossing. Okay, so we learned that single amplitude can represent a lot of different processes. So today we will talk about, we will turn the S matrix, which is represented by, if you remember, this amplitude, finite invariant amplitude, to actual observables. So we're going to turn that into actual observables. And two most important example is the differential cross section. So we're going to derive expression or like that. And then the second thing is the decay width. Decay width. That will be this. And then the connection, in order to turn the S matrix into a observable, basically we have to work it out basis. So by this I mean basically this is a question of kinematics. So we need to understand how to sort it out and set up correct kinematic discussion to turn amplitude into actual observable that we can go out and discover or test the theory. So in order to do that, let's recall a couple of things. So I'm going to so we will consider scattering process following Coleman in a box with a volume given by L to the Q. Okay, so I need to have a formulation of quantum field and associated Fox-based state in terms of this. So let's first really quickly recall that quantum field we talked about so far. So by now we should be super familiar. Alternative propagate and imposing on shell. So from now let me just on shell or just write on shell. Okay, but you understand what I mean by that. And then here normalization of the creation annihilation operator work in such a way that this is relativistically invariant normalization. And then Fox space is constructed, for instance, one particle state is constructed by acting creation operator on the vacuum in such a way that the normalization of these states also satisfy relativistically invariant normalization. So we all talked about this, okay? Nothing new. Now, I give you a name, subscript, so just so that we know what we are talking about. So the state that satisfies this, meaning the relativistically invariant normalization, I'm going to put R or sometimes Rm, okay? Relativistically normalized. Okay, just so that I know which set I'm talking about. So here I'm going to put Rm, Rn. Okay. We're going to talk about another kind. Okay, let me not mention the second kind. Let me just go back between these two, otherwise it will totally become confusing. So I want to have a formulation of quantum field in this discrete type setup. Because now I put things, yes.
So I missed this point. What is Rn?
This is relativistically normalized. Okay. Okay, good. So now let's put things in the box. So in a box, we have the following fact. Let's quickly recall. So in one-dimensional sense, obviously P dot L should be 2 pi times N, right? So if you have a cosine and sine, and you pose a sine, boundary condition, you have seen that it should satisfy conditions like that, right? So then, in 3D sense, P of x, meaning the momenta, if you put particles in the box, will satisfy 2 pi over L and then n vector, where n vector is just nx and y, and z accounts the mode, right? The n. So obviously, all of these are integers. Good. So that's vector number 1. Now I'm gonna turn this into a object that I can use in a box, and you will see why we are want to do that eventually. So we want to have dimensionless creation and annihilation operators, which I'll call P, and then I put D. So here I'm going to use bigger. I'm going to put here D to stress that this corresponds to discretized annihilation. This corresponds to for things happening in the box where everything is discretized like that. So that's why I put D here. Okay. So whenever it's D object is for things in the box. If you don't see for Rn, this is the usual relativistically invariant notation that we've been talking about. Okay, so I'm going to connect between these two. So how do I do that? Well, in order to do that, let's recall the following thing. So if you have a space-time volume V, okay, so this space-time volume, that is V31 times 1, right? V3x integration with the weight 1. And then I can write it as V3x into I momentum, which I put 0 momentum and s. Okay? But then by Fourier transform, you know that is nothing but 2 pi to the cube delta function where momentum is equal to 0. So whenever you see momentum delta function, that's V. Okay? So with that, I can generalize it too. So D times T, this is going to be now D34 1. That means by Fourier transform, it will now not vector, but 0 dot x as a 4 vector sense. Okay, so these are 4 vectors. So that is the same as therefore the space time volume is the same as 2 pi to the 4 delta, where mu is equal to 0. Okay, so this is enough ingredient. Now we can turn this into a description in a box. So let's do that. So the first thing I'm going to do, like I said, the key point here is that I want to have a dimensionless creation and annihilation operator. I will explain why in a minute why that's useful. So basically, let's look at this, or let's look at that. So then I can write it as follows. So alpha T alpha Q is equal to. So first of all, by this, and then that thing in quad, because it's almost incorrect, but I'm putting it in the quad because that's like V volume, and then so this is chronicle delta where it's 1. This is dimensionless. And this is the same. 0. And then I want to have, the goal is to have the discretized guy, which is dimensionless, just to satisfy this relation. So these are dimensionless, so that I should get the right hand side of that equation is also dimensionless. Okay? So by relating these two, I'm basically reading this as that equation. You see that alpha P can be understood as square root of 2 energy, square root of the volume of the space, and then the discretized creation and annihilation operator. Okay, so this is basically doing the dimensional analysis. right? So by just reading off that thing. Clear? Okay, good. So that is the key equation. So then I'm almost ready to write down this equation. So in order to do that, I need to do one last thing. So what is that sum over this region? I need to turn this into sum over mode. The summing over the momentum is the same as sum over the mode, right? It's the integer mode. What is that thing? Well, you know what that thing is because you know what P is. So the P is that. So small variation of that is hopping this integer lattice by 1, right? That's what it is. So you're summing over that entire thing. So this thing is the same as pi to the cube divided by volume because I have a 3 momenta. So I have to cube the prefactor and summing over this momentum, the lattice, modulus. Good. So by combining all of that, now I can turn this into a discrete program. Let me do it. Okay, so this will become, if I put in the box, so first of all, that factor at a 2 pi cube. Well, if you like, I just do it. Let me just do 1 over v sum over mode, and then I have 1 over 2e, and then the continuum relativistically normalized creation annihilation operator in terms of that thing. So that is square root of the 2 e, v, and then a discrete version plus Hermitian on chat imposes. So field in discretized version by canceling that, see that sum over mode number, square root of 2e, square root of v, then creation and annihilation. Okay, so this is the field I'm going to use, and this is the field you can take, create a box space, say in Hilbert space. Good, good. Any questions so far? Good. So I just literally, discretize the system. That's all I did so far. But it's useful technique to know, right? How you do it. Okay. So with that, now I'm going to move on and define a transition probability. Now, what is useful to define a creation annihilation operator, which is dimensionless? This is dimensionless. So why is that useful? So in order to do that, let's recall what was the S matrix. The S matrix was defined as the final state S, or if you like, you want to look at the non-trivial guy, I, and then in this case, everything was defined in terms of relativistically normal. Right? So that's how everything was defined so far. Okay. Now, if you recall, one particle state in relativistically normalized state carries a dimension. For instance, this is like the 3p momentum, and then 2 times d. So it has a dimension plus 1, and then minus 3. So it has a dimension minus 2 overall, which means that each state carries non-trivial mass dimension, in this case minus 1 as you see. Okay? So why this is not so useful? I mean, this is the correct definition physically. If at the end of the day, we want to get a transition probability. And probability is a number, right? This is a number, like probability hat, 50%. And number means it's a dimensionless quantity. So you want to be able to define the probability amplitude or probability from an object that looks like this, which doesn't change its dimension all the time by just adding more state in the final state, for instance. Right? Suppose you look at the two to the scattering, you look at the case where there's a 2 particle produced, and you do the same experiment, and another time you produce like 3 particles, 4 particles. Every time you add extra particle state in the final state, for instance, because those states carry non-trivial dimension, this object will carry different mass dimension. Every time you have to fix that to convert that into probability, which is dimensionless, right? However, if I know how to define the state which doesn't carry any dimension, then the dimension of that object would not change if I have like two states, n particle state, m number of particles, doesn't care. Okay, so that's the virtue. That's what's nice thing about using this dimensionless quantity, because in terms of this, I can define a discretized state in my box space now, and I just can define that like that. And obviously now this is dimension, because now if you ask, P, Q, D, D, that just satisfies delta Q. Nice. So it's just dimension 0 objects. Therefore, physically, now if I look at the process, something like two particles colliding, n particle coming out, even if I look at the different number of final state particles, I still get the same dimension. Okay, so with that in mind, now I'm gonna define carefully transition probability. Okay, any questions so far? So all I've done is I discretized the system. I just motivated why it is useful to consider dimensionless operators and dimensionless state. That's all I have said so far. Yes.
디스크리타이즈를 안 하면 디멘션이 무조건 있는 건가요?
Sorry, can you say that again?
디스크리타이즈를 안 하면 무조건 디멘션이 있을 수밖에 없어요.
I mean, it's a choice in the sense that even without discretization, in principle, you can try to define the state which doesn't carry dimension. What makes easy to do it with discretization is that V is a finite number. So I can put some V, factors of V, to define what I mean by that. But in the continuum limit where you send the V to infinity, everything blows up and you don't know what you're talking about. So in a sense, you can view this as a regularizing the picture. I mean, you know what I'm saying? So it is in principle possible, but it makes it trivial or easy to do it in a finite box. Any other? Yes.
So you said you want to take the B goes to infinity, but doesn't that mean that the phi will all just go to 0 at the B goes to infinity?
Here. Well, let's see. So, okay, you're saying that because of that factor, wouldn't that go to zero? That's your question.
No, you take B goes to infinity.
Well, you see, if you ask equal time correlation function of that thing with its conjugate momentum, you know that there is a delta function coming out of it, right? So if you look at the same point in the space, you know that it blows up. So that blow up factor, anyway, we know how to deal with it. So that feature, artificial zeroness, is basically a feature of that thing. Okay, so formally we define it, then we're gonna take the B goes to infinity limit. But whenever you see either 0 or infinity, we already have seen that in the continuum description in the form of equal time commutation relations. Okay, and we know how to deal with it. I mean, basically, it just meant that we just use the delta function normalization when we say either 0 or none, right? So in that sense, I don't think this is an actual issue, but it's a regularized feature. Any other question? Good. Let's proceed. So let's define a transition probability. Okay. Okay, so one thing that you want to remember is this. So let me write it down somewhere. So I'm gonna write it down here, so that we're gonna have to use it. So by comparing that relationship, what you see is that P with a relativistically normalized state in the box space is related to square root of 2e, square root of b of P discretized version. Okay, so that relation is literally from this. Okay, by excellent value. So let's remember this. So with that in mind, now let's define that thing. So now I want to look at an object that looks like this in quote. So I want to look at that something that looks like this. Okay? In such a way that, remember, what is this? This is dimensionless. Okay? And this, now, if I use dimensionless state, this is dimensionless. Great. So this, at this point, if I put pause, it's going to be dimensionless, but there's some subtlety that I have to discuss. So it looks like it's reasonable to look at object like that. So this straight gives me the notion of a probability, right? If I square it doesn't carry any mass dimension. All right. Now let's note the following three facts or a couple of facts. So for the final state particles, we basically use that. So for each final state particles, like P discretized, we will get square root of 2e, square root of b in the denominator, and then relativistically normalized. It is literally that. So for each final state particles, I'm gonna use this relationship. Okay, so this is dimensionless guy, and then I can turn that into a relativistically normalized state. So why do I want to turn it that? So this is object with a d there that I'm interested in looking at, because that gives me probability. But in order to make contact that object, which is a probability density, to a S matrix that I need to know how to convert this into this, because that was the definition of S matrix that we have defined for. Okay, so probability in terms of S matrix, that's the question. So I need to know how to convert the state, which I know for final state particles. Clear? And again, the virtue of that thing is that it doesn't matter how many particles included into here. So you can do one particle, two particles, and particle, doesn't care, because this is dimensionless guy. And then I know how to convert that into this object. Good. However, there's a subtlety for initial state particle that I need to discuss. The final state is clear. Initial state is a little bit subtler, and I will explain, and then hopefully it can clarify. Now, we want to consider two kinds of initial state. So we want to consider two kinds of initial state. Let me just put it here. Number one, we want to have a single particle initial state. And here the relevant physics is decay process. So I want to prepare a single particle, put it into the box, let the process happen, whatever it can happen. So in this case, maybe the single particle state to be the same single particle all the way time without nothing happening, right? Without having anything on. Or the single particle can turn into something else. So the single particle decay into something else. Okay? So that's what we can do. But then what is the physics input that you need to remember? The difference between initial state and the final state is the following. Initial state, you prepare actively, right? You prepare something in the lab and let things go. And you should know that particular configuration with 100% certainty. Okay? So initial state is characterized by the fact that I know there's a one particle in that one box, for instance. And then letting something happen. But final state is not like that, right? Something happened and something can create. And those are final state, and you have to take into account all possible creation of final state probabilistically correctly. So the real difference is that in this, for instance, single particle case, the physics input is the following, right? For instance, there is a one particle with the probability equal to 1, meaning I know it, in a box with a volume V. Right? So that's the experimentalist understanding or knowledge about the system. So how do I understand this thing? How can I convert that in terms of necessary normalization for the initial state? Okay, let's talk about it. So what that means is the following. So in this case, you can guess whether the reasonable option is that, because we already know how to define dimensional quantity in such a way that the norm of the initial state, which is basically that, which we define with just one, right? That's how we constructed this discrete type state. But let's understand this slightly better. So remember this, let me write it here. And let's make this statement sharper. I'm going to convert this in this form. So P, this rectangle sense is the same according to that knowledge. It's the same as pairing it. So 2E, 1/B, and then that thing. So that thing satisfies normalization that looks like this. And then 2 Is that clear? So I just computed it looking at that. Why did I do that? To extract the physical meaning of that same. So it's one, but like, what does that mean? It's one physically in the context of that set. Okay, so 2E factor drops out. So what they mean is that I told you this is volume, but it can be understood as integrating over the box in this context. So what it means is that integrating over the box with the volume B and then order B. So in this case, the statement that the distance is normalized to be 1 is the same as saying that the probability having a particle in a box is 1/B, and then you are integrating over entire volume, so you get just 1. And that is the same statement as saying that in the box with the volume B, I know there's a 1 particle somewhere. That's what that statement is. Okay? The probability density integrating over the volume. Okay, so that's great. That seems like a good choice because I think that's exactly physically how you want to prepare, right? In the box B, with 100% certainty, I want to put some particle there and let something happen. So this is a good choice. This is a good choice for one particle state, right? Now let's proceed. Let's consider the second possibility. That's the first one kind of initial state that we want to talk about. There's another class of state, initial state. And that is two particle state in the initial state, and that is associated with the 2 to n scattering process. So this is the decay, that is the scattering. This is what people do at the LHC. Okay, they collide a proton, which is two particle state, and then boom, a lot happens with all possible numbers of that. Okay, so then again, let's ask, what is a good choice of initial state? In the sense that the physics makes sense. So I might try, okay, in this case, can I just take exactly the same way? P1, P2, D. Sounds like a D, that's a good choice. Right? But let's ask. So for each of those, one particle state, we know that probability density being 1/B, as I just analyzed. So in this case, if I ask, okay, I'm gonna integrate over entire volume of the box, and then I want to ask, what is the probability of finding one particle and another particle in the vicinity of the first particle? Because I want to prepare the initial state in such a way that they collide. Because that's what we as engineers can prepare. So, but if you naively do it, okay, is the first particle probability density, second particle probability density. If you do that, that's 1/B, which goes to 0 if you take volume infinity. Which means that if you naively normalize your two particle state like that, most likely the collision will not happen. And that's not the initial state you want to set up. You want to set up in such a way that there's a 100% chance to collide. And then you ask what final state, right? That's the meaning physics question. So here, therefore, the physics statement is the following. I know that there's a one particle. So let's call particle number 1. Oh, that's not good. P1 with probability 1 to be in somewhere in a box. So that's the first part of the talk. First part of the argument. And and there is a second particle. With probability 1 to be in the vicinity or neighborhood wait neighborhood. Good. Good. Oh, P1. Okay, so I want to, oh, not 2 like that. Okay. So I want to be a situation, I want to prepare you in such a way that the second particle, I know 100% certainty that this guy is basically on top of first particle. Because they have to collide. How can you make sure that? If you put just the one particle of the second kind in box B, then every point has a probability of finding an order of unit, right? Not one. So what do you have to do? You have to put basically, in a rough sense, V number of second particles, right? So every point in space and time, you see one such second particle. Okay? So that means this motivate that of here. Oh, sorry. There's still. How do I lower this thing? That's no. No, I do this. I'm sorry. Yeah. No. In case somebody cannot see what I'm writing here, that's what I'm trying to go. Yes, we're getting at. It told me I have to click on it, right? This button doesn't work. You get my fault. Oh, very good. Thanks. You. Okay, so let's continue. So, in order to prepare initial state that satisfies this criteria, meaning 100% chance of collision, that's the criteria here. The correct normalization is not just that, or actually there's a B, B1, B2, B, so that if you now look at the normalization in the following sense, you're gonna get extra B, you square that thing, right? So that becomes 1 overall. Is that clear? So that's the right decision. So you see, now everything makes sense, great, except the fact that there's a little bit of a subtle, careful thing one has to take into account. Okay, because here, depending on whether it is a one particle initial versus two particle initial, there is a slight factor of difference. This is totally dimensionless, but this carries dimension now. But that you have to do. Otherwise, you're not setting up the initial state that you know they're going to collide. So you have to do it. Good. Now we are almost ready. Good. So let me summarize, therefore, the discussion for the initial state. So initial state, therefore, for each initial state particle, what we have to do is that for each initial state particle, I have to use this relationship because I'm going to express everything in terms of the dimension of this particle state. And so we have to do square root of the T initial state. However, for one particle, I can just use that. So there's a 1 over square root of the B. For two particles, naively, there's a 2 factors of square root of the 1 over square root of the B. But I told you that there's another factor of square root of the B. They cancel another factor. So overall, where is it? You're gonna have this times 1 over square root of the B for both 1 and 2 particles in this state. Is that clear? For one particle, just because of that. For two particles, I get another factor, but there's another factor that cancel out one factor of that. So overall, it turns into this. But for final state, I can just do it for all such states. Okay. So if you get this part of the discussion, I'm ready to write down an equation that basically equation for transition probability in terms of estimates. Let me know if you need any clarification. I'm gonna erase this part. I'm gonna write down that master equation. Are we good so far? Good. So I am interested in D and G. And for each of the final state particle, I will have that factor. So I'm just gonna remind you that for each final state, I have 2EF go to the V. And for each of the initial states, I have square root of T5. There's only one universal one of square root of D factor from the initial state. This is final, this is initial. So I converted the state into a relativistically normalized state. The times what I get is F relativistically normalized, I relativistically normalized. Right? And that is S matrix, we know. Right? So and this thing is nothing but we agree to write it as I times Fi converted from I to F. This is invariant phi one amplitude, and then 2 pi to the 4 delta momentum under delta function. But here I'm gonna just write down this superscript as the formula D, just to make sure that this is defined by putting the system in a box rather than defined as in a continuum limit. Okay? And the relation is going to be if I take V to infinity and T to infinity by taking the continuum limit, this amplitude we convert into regular amplitude that we have been talking about and computing a lot of those objects. Good? Yes.
Why when T goes to infinity?
Why am I thinking about infinity?
Yes.
So, because that's how we also, sort of formally define asymptotic state eventually to send all the external lines to the infinity.
Then are you saying that just a PD or FD or ID was not at time infinity? At the outside expansion?
How do you mean this?
Yes.
So they are asymptotic states, right? As we define, right? And then S operator was appeared as a unitary rotation that converts, say, asymptotic in state basis into the asymptotic out state basis, right? So in that sense, yeah, those are. But I'm saying these relationships, if you look at it, there's all specters of V and not. This is defined in a box. And then in principle, I also regulated the time in order to avoid any infinity that comes from this. You will see momentarily that we will immediately get the expression that does have explicit T in it. So if we didn't regulate the T part, as you will see momentarily right after this discussion, then everything will be just infinity. So basically, I'm putting the system in the V finite volume, and I'm just looking at the system in a finite time interval, and then I'm just gonna take the limit where after I obtain the result that looks interesting and meaningful. So basically, we are doing regulated computation for that. Good. Another question? So with that preparation, we are ready to write down transition amplitude. So what's that definition? Transition probability is fixed. This is important name. This is keyword. The fixed initial and final state momentum. So now, honestly, momentum is given by this square of the state. Now let's look at how they look like. So they would look like. So for each final state, I'm gonna have 2E times B. And then for each initial, I'm gonna have E. And then overall factors of E so far. And then I'm gonna square this object. So that will be absolute value of P squared. And then you have two factors of that thing, right? So first you have 2 pi to the 4 delta 4 T this. But then if you have a square of that thing, one enforces the argument to be 0, the other vice versa. Okay, so that means that basically you have another factor that is basically this. So here what I just said is that if you have a delta of x, delta of x, then the same as delta of x, delta of 0. Same result, because this is not zero only if x is not 0. Vice versa. You can always write this way. And if you remember, what was this? This was a force, space, and time volume. So it's a V times T. So naively, therefore, if I didn't regulate the space volume and the time, everything blows up in crazy sense. Right? Now you see exactly where the infinity comes from. Okay? Now, I need one last ingredient to write down the meaningful transition probability. So this is the transition probability with the fixed final state momentum. So what that means is the following. You say, put one particle at the decay, and then a lot of particle comes out. And then you're observing a final state particle with a particular momentum. You ask what is the probability of that? But in reality, in the experiment, what's going to happen is that if you prepare some initial state, either decay or scattering, whole bunch of things can happen. And then many with the fixed final state particle, they can carry many different kind of momentum configuration, right? Like electron particle coming out of the process, they can go like that, they can go like that, and the one guy carry higher momentum, the other, and so on and so forth. So you have to factor in this different possible momentum configuration. So in other words, we have to factor in what's known as a density of state of the final state, particle state. So we fix the size of the momentum, how many quantum state that there is associated with that simultaneous momentum. So if there is a 10 actual quantum state for fixed momentum versus only one, obviously there's a higher probability to happen for 10 final state, quantum state case. So we have to take into account this density of state. So that's the last ingredient. And then we can combine everything to write down a transition probability. So that final state density of state. And that's sort of easy to take into account. Why is that? So we already know that P is equal to 2 pi over L N. Right? So what it means is that the number of state, the quantum state, with the fixed momentum is given by V over 2 pi Q. And then say summing over that particular one is the same as D3P momentum. Is that clear? So that was exactly counting number of quantum state for like fixed P and in the vicinity of that thing. Right? So this is the density of state. Okay, so therefore, now I can write down with this, I can write down a differential transition probability is equal to that thing multiplied by that final state density of state. Final state density of state, yes. And so that will be, let's write down. For every final state I'm gonna have. So I'm gonna combine that factor with that factor, right? For final state. This is for final state, remember. I'm looking at what are the number of final state particles in this little volume in the quantum state space. Okay, so that I multiply that together with that. That's the final state factor. So that's 2, now bar, I put it bar, F over 2EF, because volume factor cancels. Great, so that's the final state. And then let me put momentum conserving delta function together here. Okay, let me continue to write. And then for initial state, there's a 1/2E factor. Good. Now, that volume was canceled by that volume. This volume, let me cancel against that. Okay. And then this is initial. And then there is this square of amplitude times T. So we're gonna organize as follows. Put everything here. I'm gonna call following comma, which is physically nice packaging. So let's understand this expression, and then we're gonna have the differential probability. So I prepare an initial state, either single particle, two particle, and then each initial state calls that factor. Okay, and then we will see that this 1/2 is extremely important and the reasonable thing to have. We'll see. Then I let the process happen from the I to the F, which is controlled by this invariant Feynman amplitude square, which we know how to compute it by using Feynman rules. We talked about it. And then I produce a final state. And then for final state, I have to basically take into account all possible momentum configuration. But they have to satisfy the momentum conservation, energy momentum conservation, right? So boom happened, and then a lot of stuff coming out, and then I have to integrate over all possible quantum state, but with the constraint that energy and form momenta are conserved. And there's this large peak, right? This is the entire time. So if I want to have divided by differential probability, transition probability per unit time, this is noted. Okay, so this is just general expression. Okay, so that's our master formula that you're going to play a little bit. Question. So run through the discussion I just gave you. What did I do? Right? I wanted to compute the probability, transition probability. For that, I thought it's better to have dimensionless quantum state. So I put things in the box, and then I have a relation between relativistically normalized state to a dimensionless state. So for every final state, that's great. Because even if I change number of final state particles, dimension doesn't change. That's great for probability. On the other hand, for initial state, there's an actual physics picture in it, which means that there's a 100% probability for a particular configuration of preparing it. So for instance, I know that there are two particles. Not only there are two particles, I know that there should be 100% collision. And then I'm asking what is the transition probability. And there was a little bit of some discussion, factors obscure the B because of that. But if you take into account, and together with the fact that there's this density of state for final state, then you arrive at this formula. Now, this is true even if you now set the T, B goes to infinite limit, because this is completely regulated. You don't see any B, you don't see any T in this equation. Okay, so that's a quick summary of what we have talked about. Now we're going to use it to do some physics. Okay, so now let's actually use this math problem. So therefore, here is I'm just going to write that expression in a compact way, and then we're going to play with it the rest of the expression. There's a differential transition probability per unit time that's equal to basically amplitude squared, and then for initial state there is let me just write D, and then for initial state we have to pay the price of 1 to I. So that's the math formula, and then let's consider two separate cases. Okay, so let's first talk about when initial state, just that. So I have a single particle, and we are talking about the decay process. And in that case, the differential transition probability per unit time for decay process is obviously called differential decay width. And decay width is written as a d of gamma. This is symbol for the decay rate. And from that, now I have a single particle in the initial state. So I will have just 2 times d for the initial state, and then transition amplitude for the decay, and then we have d. Right? The relativistic final state sensitive state, the d. Okay. Else, this is basically what it is. You sum over all possible final state momenta, but you force the total energy moment conservation. And this is totally Lorentz invariant, by the way. Hope you see. This is totally Lorentz invariant. This is great. So this is Lorentz invariant. This is Lorentz invariant. And D, first of all, we know that this is Lorentz invariant measure, right? We talked about that. And this is also manifestly Lorentz invariant because this is in terms of core momentum. If you have core momentum difference, if you do make any Lorentz transformation, it's the same thing. Okay? So this is the manifestly Lorentz invariant. And this has a name called invariant Feynman amplitude. And secretly, or maybe explicitly, this is Lorentz invariant. You might think that you don't want to take just because of names. Let me give you a quick answer to that question. So where do they come from? They come from by looking at transition amplitude, where S I define as 1 plus IT, right? And you look at this, and then there's factors of I because of factors of I. So there's amplitude, and then this. That was how this was defined. Now, that is obviously Lorentz invariant. So if this is Lorentz invariant, this is Lorentz invariant. Right? And what was that? This is exponential of manifestly Lorentz invariant Hamiltonian. Right? So that is Lorentz invariant. This is Lorentz invariant, or this is Lorentz invariant. That's why it is the name. That's why it is called invariant amplitude. So everything is invariant except this prefactor, this factor. Okay, so this will control, this will determine how a given rate transforms under Lorentz transformations. Okay, anyway, I wrote it down here. So that's the answer. Now, let's check the mass dimension of this object. Let's check the mass dimension. It's always healthy to check the mass dimension whenever you have some expression to get to know what you are talking about. Okay, so that's the chapter 1 in physics 101, right? Like units. I was mesmerized when I first read that when I was first undergrad. Wow, I feel like I'm doing physics. Like, you know, I don't know nowadays, but there was certain discussion in that book that I was reading that, you know, let me give you this nice looking equation. You can tell that this is immediately nonsense by just checking unit of both sides. If they don't match, you know this cannot happen. It was like, wow, amazing. I can do something with it. So same. So let's check the mass dimension of this. So the answer, so mass dimension of the gamma you want to achieve is 1. Okay, so let's see how that comes about. So in order to do that, you need to know the dimension of that, dimension of that, dimension of that. Great. So let's check. First of all, what is the dimension of U? So let's consider arbitrary NF number of final state. I wrote down here. So this is dimension 2 of it, right? 3 minus 1. And then I have NF number of them. So this is 3 times NF. So there's a delta function in momentum space, which is minus 4. Good. So therefore, this thing has a dimension of 3. No, did I say 2? 2 minus 4. Yes. Are you with me? Yes. Good. Now let's check the dimension of this thing. So in order to check the dimension of that thing, we have to write down the definition of that thing. So final state in the relativistically normalized one, f minus one, initial state relativistically normalized one is equal to well, I this and then 4. What else? Right? Excellent. This is correct, but in order to really figure that out, it's better to look at the thing that I wrote before. So I want to look at an object in terms of D. D. Oh boy, I have to rewrite. So we construct this, and that looked like for every final state, we had 2E final, B, and for all initial state, we had E, and then a single factor of x to B, and then there's I, B, T, factors of I. And then what? Momentum vertical. Right, so that was the expression I derived. So this is manifestly dimensionless, right? This is dimensionless, and I'm talking about decay. So this has dimension 0 if it is a single particle, like single particle. So for now, let's just focus on this case. So the left hand side is a 0. The mass dimension is 0. So okay, this is what? Minus half, and then that thing is 3 half. Because it's volume, but volume is opposite of the mass dimension of volume is opposite of the momentum, right? And then I have an F number of that. And then this is minus half, but I have only single particle in initial because I'm talking about decay now. And then there's what? That thing is plus 3 half. Very good. And then dimension of A minus 4. Okay, so 0 is equal to, you're gonna help me. And you're not gonna. Are you going to? I don't hear anything. So this you can. All right, so let's put it here. Good. So therefore, dimension of gamma is equal to -1 plus dimension of that thing squared. So that is 2 times 3 minus NF. Dimension of D, which is what? 2NF minus 4. And hopefully that adds up to 1. Yes?
Yes.
Done. So okay, so decay rate has dimension 1, meaning it has a dimension of energy, which means that it has a dimension of 1 over time. Okay, so for this, can you see if I write that here? Okay, good. So gamma can be written as 1 over tau, the time scale, and tau is particles mean flight time. Meaning the fact that gamma is large means that decay happens a lot of times. Its probability is very large. That means that the particle lives very short. Good. If it is very small, it takes a long time to decay, which means it's long-lived. Good. So that's the relationship. Now, before I finish, let me finish up the discussion with the 2 particle initial state, because I already wrote down this expression, so I want to recycle it. Okay, so let's do the same thing with 2 particle initial state. So everything is the same. Now, instead of that, for 2 particle state, we have extra square root of the V vector. Remember that? That means I have minus 3 half. Good. Square root of V, which is 1 over momentum cubed to the half, right? Good. And that thing is equal to, here should be the same, except the last factor. So let's do it. So NF, and that's just NF. That's NF, that's the same thing. And then what's different? What's different is 1/2 times 2, because I'm talking about 2 particle initial state. Okay, and then plus 3/2, and then amplitude minus 4. So in this case, amplitude for two to the n scattering process as a dimension of basically you have half more, right? Because instead of one, it has another half minus half. You have half more. That means 7 half minus half. Okay, good. So I have done it. So I'm gonna write it down here because I have to use that. The dimension of amplitude when it goes to 2 to the n is 7 half minus n. Good. Then we're gonna use it momentarily. Okay, so this is decay rate, and then now you are almost ready to compute once you know how to do this momentum integration. Okay, which we will also discuss. But before that, let's understand the physics meaning of this formula a little bit more. Now, I told you that this is Lorentz invariant, this is Lorentz invariant, this is the only physics which is not Lorentz invariant. Okay, so the decay rate is not Lorentz invariant. Good. Are you panicked? No. Are you okay with that? How do you feel if you have observable which is not Lorentz invariant? Are you panicked or not? Panicked? Absolutely panicked or not? So in probably second year in undergrad, right, you learned this modern physics thing. And then one of the first thing appeared is time dilation. So if you have a particle and then it goes very fast, it is known that it has a longer lifetime. Okay? So I told you that the connection between gamma and then lifetime here. So let's check whether it works out that way. This one. To do this, let me define a d gamma at rest. Meaning I just go to the frame where a particle sits at rest, and then I'm just waiting for that particle to decay away. So in that case, in the rest frame, everything is same except that this is a fast decaying particle. Right? And so gamma divided by gamma rest, if you like d, is what? M over EP. Yes? And then remember that energy can be written as that. And then this gamma is, oops, now better not close. That will crash special relativity. Right? And gamma is greater than or equal to 1. Yes. So now let's check whether that makes sense or not. So in terms of, so that is the same as tau rest divided by tau with some momentum carrying it, because gamma is inverse of tau. Right? Are you with me? Good. So that means tau is equal to gamma times tau rest. So is this what you expect to see? Okay, good. So therefore, it all makes sense, and decay rate indeed satisfies time that relation as it needs to be. Oh, no, that side is important. I better write the page. Okay, any questions so far? Good. Now I'm going to derive an expression for a 2 to n scattering process. So we covered and list formally how to compute the decay rate. So let's not talk about the scattering process. And I want to keep this part, so I'm going to erase here. So let me start this question here. So 2. I want to look at the 2 to n scattering. And for that, my initial state is 0 to the v, v1, v2, v3. So in this case, what I am interested in is the differential transition probability per unit time per unit flux. That's what I am interested in. So we computed the so-called differential transition probability per unit time, and I would divide that by the unit flux. So let's understand why we are interested in this one first. Okay, the situation is the following. Suppose you have one particle and another particle colliding each other. Okay, so that's basically what's happening microscopically. But really, what you set up is the following. So whenever you have that situation, first let's talk about just two particles. If you have a particle 2, particle 1 that head on each other, then suppose that thing has a v1 velocity, you think this thing has a v2 velocity. You can boost this system back in such a way that P1 is at rest. Okay? So I just gonna make a Lorentz boost the entire system and bring it to the system where P1 is at rest. That means I can go to the frame where P1 sits at rest. And then this guy is just trying to go with the velocity V2 minus V2. Right? And then you ask, okay, for each of those incidential particle, the particle that is incident on the P2, and then when it collides, a lot of things will come out like that. Right? So the physics question that we are interested in is for each such P2 that actually managed to collide with the P1, what is the probability for like final state that I've observed? So in this case, this factor must be included as a part of the probability. So that's where this unit flux part comes in. You see? So if you throw in hundreds of them versus millions of them, obviously you get to observe many different, very different probability distribution. So sorry, I said this wrong. If you throw in 100 versus million, obviously the number of events you measure will be very different. Since we want to get the probability, I have to multiply by the number of incidental particles. Okay? So I have to ask the question, for each incident particle, which I just phrased as per unit flux, what is the probability, right? That's how we have to phrase it. Okay? And then if somebody told me that, oh, I actually throw in billion particles, I just multiply by billion. Oh, actually, I just throw in only one particle, I just multiply by 1, right? So we want to have that normalized probability. So to that wording, this can be written. So this is written as the little sigma. This is the notation for what's known as a process. Okay, for 2 to n. And that thing is written as, oops, now I'm squeezed. Yeah, so now I have 2 particles in initial state. So I'm gonna have like 4 E1, E2, which is 2 times E1 times 2 times E2. Okay. And then I have this D. Okay, so that was overall factor times this unit flux factor appears as a 1 over V1 minus V2 velocity. So that comes from the unit flux factor. And I know you're not happy if I just write it down. Okay, you need to explain why that's the correct factor. So let me quickly explain that. Do you have a question? Am I going too fast? Or good?
A little bit less.
A little bit fast. Thanks for being honest. Yeah, I need input. Okay, because I want to get to the LACZ, but that's my personal goal. Any questions so far? Let me take a pause because I realize I'm maybe going. Okay, so everything makes sense except that factor, right? Because I already derived that factor other than this. Let me just explain. So particle flux particle. Particle flux is uniform particle per unit area per time, unit time. Okay, so in other words, in that picture, say, so suppose the target particle associated with some cross-sectional area A. In other words, if you try to go that way, you see this area. You can imagine that as a ball, if you like. Okay? So if there's a ball, classical picture, there's a cross-sectional area, right? And then there is a bunch of, there's a particle bunch, if you like. This E1, E2, and then this is about heading on to that. Okay, and then this velocity that I explained to you, I can already speak as we did because I just go to the red triangle target point. And then so for each this given area, how many collisions you are actually having per unit time? That's your measuring. Okay, so in this case, therefore flux, you're right. The flux is suppose I have a density rho of P2. Okay. Yes, you're preparing just the single particle P2, but imagine there is a bunch of P2 particle with a density rho filled into this box with the volume P. Okay. So that means if I wait for time t as this guy crossing this one, then total number of P2 particle that passes through the target particle is density times volume that sweep through this thing. So it's rho times volume. But then rho volume is what? Like area and then that length, which is controlled by V2 minus V1 times V. Okay, so that's length. And then divided by area times T. Area times T. So you get that this is nothing but rho times V2 minus V1. It makes sense because if you pass through much faster, then obviously way more particles will collide onto the target particle. So flux goes up. Now, what about the rho factor? So rho factor, we have to factor in the square root of the V. If I explained to you what that square root of the V meant was that if I look at the volume, the first particle, the probability is 1 over V, right? And the second particle, I believe 1 over V, but I said I'm gonna just throw in V number of second particle, right? So then the what is rho? Rho is given V, how many second particles do I have? What is the number of second particles do I have in V? That's like V. Okay? So V over V is 1. So it means that basically there's a unit density. That's how we prepare the initial state. So I mean effectively, so this is effectively that. Now you might say, oh, I'm not happy. I talked about this unit, I told you that I felt so great that I can deal with the unit, but that's like I totally messed up the unit. Right? Rho is supposed to have a unit of 3. Well, this is dimensionless. What am I doing? Secretly, what you're doing is that when if you have defined everything here that we beautifully define in terms of that state, right? That you would have 1 over V up here secretly, unregulated object. And then if I just honestly do it, I will have here appearing like that over V. That's the flux, 1 over V. So they would cancel each other. So I just reshuffle things a little bit without worrying too much about actual dimension of it. Because when I define initial state like that, obviously I a little bit screwed up the dimension. And then here I also a little bit screwed up the dimension too. But I'm saying I screwed up exactly in such a way that they're canceling out each other conceptually. Is that clear? So therefore when I say this, I really meant like V number of P2 particle without worrying too much about dimension because I know that the dimension will sort it out by making good mistakes, if you like. So anyway, so with that, hopefully that makes sense. I dropped the V. So this is a differential cross section. What is it? It is the differential transition probability, which is dimensionless, per unit time, which creates dimension 1, per unit flux. Okay, so we have to figure out the dimension of that. Okay. But I lied you a little bit because the differential transition probability, that definition has slightly non-trivial dimension with it. Oh, I see. Good. So I have to stop here, but basically you can do exactly the same check that this sigma has dimension minus 2. Okay, so I leave you that exercise to do so. And so this has the dimension of area. Therefore, it's called cross-sectional area. Okay, so I'll finish up that part of the discussion quickly next time. Then we will discuss the computation and unit errors. Right, so that will be end of today. Yeah, anyway, actually, I'll come to the rest. Oh,